In this video, I will present concepts associated with rotational, kinematics, and energy. That's Walker Check 10. So first is arc length. Arc length, we'll use the symbol S. It's measured in meters, and an arc length is a length, it's a distance, around a circle. So if I want to know the arc length between this position and this position, I can't go straight across, I follow the circle around. And it's this length, the length of the rubber of the tire, that defines the arc length. So we use S for that, measured in meters. Also, angular position, theta, or angular displacement, delta theta, these we're going to measure in radians. Okay, we've been using degrees for our angles up until now, and we'll still use degrees for some things, but when we're talking about rotational motion and solving for how things are rotating, we're going to use radians because it makes the math a lot easier. Tangential velocity. So we'll use a V sub t for that. It's also in meters per second, just like every other velocity we've learned about. So tangential velocity means at this point, how fast is it moving? Okay, and in what direction? So up here at the top, this tire is moving that direction at, I don't know, whatever speed it's going at. So that is tangential velocity. If something's spinning around an axis, the tangential velocity is always at 90 degrees to the distance to that axis. Then we have angular velocity. So angular velocity is a number of radians per second. So if something is spinning and it moves 1 radian, so 1 radian is about from here to here. So if it moves 1 radian in 1 second, that is 1 radian per second. That is the angular velocity. Tangential acceleration, that is, again, it's a linear quantity. Tangential acceleration is the change in tangential velocity over time. This reference line, this is where theta equals 0. Theta going this direction is positive, the other direction is negative. So theta is positive this way. The distance r is always measured from the axis. And the reason we use radians is because if we use radians, that makes a very simple relationship between the arc length, which is this blue thing here. Arc length S is just equal to the radius r multiplied by theta. So this is measured in meters, r is measured in meters, theta is measured in radians. When something is turning, it's very common for us to talk about the counterclockwise direction. Counterclockwise is opposite the direction that hands on a clock go. So you can draw an arrow curled around to show the direction. You can call it counterclockwise. Also, the positive direction is the counterclockwise direction. So you can say positive, you can draw an arrow this way, you can say counterclockwise. Those all mean exactly the same thing. There's also another way to do it. This circle with the dot. I'll explain that in just a minute. So this side is the exact opposite. So something going this direction, that's the clockwise direction. We can also call it negative, or we can draw a circle with an X. And what that means is, if you have an arrow, so we can draw arrows pointing left, right, this is a curved arrow. If there were an arrow pointing straight at you, you would see the point of that arrow. And that's what this is supposed to be. So this is the shaft of the arrow, you can see the point sticking out at you. So this is an arrow drawn pointing out of the board. This is an arrow drawn pointing into the board. Because if you were doing archery and you had an arrow from archery and you turned the arrow to face the other direction, you would see the feathers on the back of the arrow. This X is supposed to look like feathers on the back of an arrow. So this is an arrow pointing into the board. The reason why it's in and out is due to the right hand rule. It's important that you use your right hand for the right hand rule. So I'm going to put my left hand in my pocket. And if you're sitting down, you might want to just sit on your hand so you don't forget which hand you're using. So right hand rule, if I make my fingers curl around in the direction that this arrow is going, so my fingers curl that way, my thumb is pointing straight out of the board, the direction of this arrow. So this direction, my thumb points out, that's out of the board. This one, if I point my thumb into the board, my fingers curl that way. That's why this direction, so an arrow pointing in, you could call it into the board, you could call this out of the board. So these are now 4 different ways that you can describe the direction of rotational motion. I don't care which one you use. I do expect that whichever one I use, you'll know what I mean. So I may describe it in any of these ways. You can use any one that you want. So on a quiz or a test, if you say counterclockwise, that's enough. If you draw an arrow like this, that's enough. You just have to use one of these, whichever one you're most comfortable with. Next thing, moment of inertia. This is an I, so moment of inertia is a capital I. It's measured in kilogram meters squared, and moment of inertia is a resistance to rotational motion in the same way that mass resists linear motion. If I push on something that has a large mass, it's hard to push. It doesn't speed up very quickly. Same thing. If something has a large moment of inertia, it's hard to make it turn. So it's very slow getting started to move. So that's what moment of inertia refers to. And then we'll also have rotational kinetic energy. This is now another type of energy that when you're adding up all the types of energy in a system, you have to add in rotational kinetic energy. It will be K sub R. And as with any energy, it's measured in joules.